In this video, I want to go through the titration of a weak base. I'm going to use hydrazine here, N2H4, just to do something different. I've been doing ammonia all the time. And with that, I'm going to do it again before, at, and after equivalence point. And this time, I'm going to go pretty quickly, and I'm going to do all the calculations sort of in parallel with each other. So we're going to do A, B, C all in one step. I just want to illustrate sort of what's going on in each situation by comparing them directly with each other instead of just doing one calculation all the way through and then doing the others. So presumably the first thing we need to look at here is the acid-base reaction between hydrazine and HCl. And I guess what's going to happen here is we're going to get N2H5 plus and Cl minus. And that way they'll neutralize each other, and the proton will be donated from HCl to NH4. Again, we always assume that this reaction happens to completion. So we're not going to be working with concentrations here, we're working with moles. So for N2H4, I have the same situation in all cases. C equals N over V, N equals CV, and in this case my concentration is 0.1 molar. My volume is 0.02 liters, and so my moles will be 0.002. Okay, now for the HCl, I'm going to do 1, 2, and 3, and I'm going to do them all right here. And then actually I'm going to switch these, because I'm not interested in the concentration of my HCl. I'm going to move my N2H5 out here so that I have space to put the resulting moles 1, 2, 3 in these different situations. Now, first of all, if I have 5 milliliters and I have 0.2 molar, I'm going to go sort of towards halfway to the equivalence point here. So C equals 0.2. That's true for all of these guys, by the way. That's the concentration of the HCl that I'm using as my to titrate this. Here my volume is going to be 0.005. Here my volume at equivalence will be 0.01. And here, going way past equivalence apparently this time, 0.15, 150 milliliters. So I can do my mole calculation in all these situations. This one is 0.001. This one is 0.02. 002. Note that this and this are the same. That's how we know we're at equivalence. And then after equivalence, 0.03. So in these three situations, I'm going to end up with a different thing happening. This is limiting for 1. So if I focus on 1, I'm going to get 0.002 moles of hydrazine minus 0.001, and I'll be left with 0.001 moles of the hydrazine in that situation. And in situation 1, I will create 0.001 moles of N2H5. Just keep all these separate. In situation 2, I will react, so this is 1. 2, I will react away all of my hydrazine. That's the equivalence, leaving me with none. And I will create 0.002 moles of this. So here I have none of my base left, and I've made only its conjugate acid. And then finally in situation 3, this will be my limiting reagent. So it'll get completely wiped out, and I will be left with a fair amount of HCl left over. So in situation 1, I had hydrazine left over. In situation 2, I did not have hydrazine or HCl left over. They both went away completely. And as a result, I created a whole bunch of the cation, the associated cation with hydrazine. And then in the third situation, I reacted away some of my HCl, but I had HCl left over, and so that HCl is going to dominate the situation. And I did create some of this, 0.002 moles of it, but the truth is, because this is weak, and this is strong, I don't really care about the amount that I created that in situation 3. Now, what that means then is in situation 1, I have weak base and the conjugate remaining. That means I have to do an equilibrium. In situation 2, I have no base or acid left, but I do have my conjugate, which is propped up, and that means I'm going to have to do an equilibrium with that. And in case 3, I'm left with a strong acid, so I do not need to do an equilibrium because it's strong, it reacts to completion, so that's actually the easiest case. So let's fire through these 3 cases, and then let's look at what the pH looks like in each. So number 1, with the weak base remaining, I had N2H4 plus H2O going to, this is the equilibrium that gets set up, OH minus, and N2H5. Here, hydrazine is acting as a base, donating its proton, or not a base, sorry, acting as a base, accepting the proton from water. So, what did I have here? I had 0.001 molar of it remaining. Now I need to be a little bit careful here. In this situation I had 20 milliliters. In all these situations, in fact, I'll have a volume of 0.02 liters associated with the volume of the original base, and I've added 5 milliliters. 5 milliliters in this case to that total volume. So my new volume is 0.025. So 0.01 divided by 0.025, and I have a concentration of 0.04. My K value associated with hydrazine, and I'm just looking at this out of a chart, is 9.6 times 10 to the negative 7. That's a KB value. Alright, I'm going to assume I don't have any of this to start, and I do need to be careful here. Through this reaction in 1, I did create some of my anion, 0.001 of it. So since my moles are the same, and my volume is the same, I can translate that to a concentration that's starting at 0.04 as well. Okay, so I'm going to assume that this equilibrium shifts to the right. And then because you can look at this as either the common ion approximation or the 100 rule, but since 0.04 divided by 9.6 times 10 to the negative 7 is greater than 100, much greater, then these x's are small, and so I can make these approximations 0.04 and 0.04. Okay, now my KB value is equal to the concentration of my hydroxide. Concentration, I don't know what the name of this cation is, but associated with hydrazine, N2H4. And so I get a K value of 9.6 times 10 to the negative 7. And here my concentration of hydroxide is 0.04. Or not hydroxide, sorry, it's X. For the cation is 0.04. And for the anion is 0.04. So those two are going to cancel out. That happens because I went halfway to equivalence. If I had been somewhere else, it would have been something slightly different, but it still would have, it would have been a multiplier, but not something that really changed the problem. So there you go, I got 9.6 times 10 to the negative 7 as my concentration of hydroxide. I can use that to find my POH. And I get a pOH of 6, which means I have a pH of 8. Okay, so that's halfway to my equivalence point. Now let's go add equivalence. So now we're dealing with situation 2. In this case, I've completely destroyed my N2H4 population. And so it's the N2H5 because it is a conjugate of a weak base that can perform the reverse reaction and act like an acid. The concentration of this, well, I'd have 0.002 moles of it created and 20 and 10 milliliter volumes respectively. So to get its concentration, I'd have 0.002 moles of it in a volume of 0.02 plus 0.01 or 0.03. And so I'd get 0.02 divided by 0.002 divided by 0.03, 0.0667 molarity. Now I've completely wiped out the population of this, and I'm ignoring the native population of that, so I'm going to assume that my equilibrium will shift to the right here, destroying x of those and creating x's of these. And I don't have my k value for this, but I do have my way of calculating it. The Kb for my associated acid, or base, is 9.6 times 10 to the negative 7, so I can use my typical expression that relates the K values of conjugates. So my Ka for my conjugate, what did I say, 9.6 times 10 to the negative 7? That's a 5. There's a 7. Yep, that's right. So my Ka value is 1.04 times 10 to the negative 8. Okay. Now, obviously my K is very small, my concentration isn't that small, so 0.0667 divided by K will be much greater than 100. So this is small, so this is approximately equal to 0.0667. And now I can write my K expression. Ka conjugate is equal to hydronium the weak base, and the ion. So these guys are both X. This is 0.0667, and this is 1.04 times 10 to the negative 8. So 1.04 exponent negative 8 times 0.0667 square root. I get an x value of 2.6 times 10 to the negative 5. In this case, x represents my population of hydronium. So I can calculate my pH directly. And that'll be 4.6. Okay, last but not least, if we overwhelm in situation 3, and this one's much easier. This is our strong acid, and we're left with this 0.0028 strong acid. And we have some of the weak conjugate, but it's going to be very small in terms of its effect in comparison to the acid, so we're just going to focus on the acid. Okay, so I've got H3O plus. I have 0.028 moles of it remaining in my new volume. I have 150 milliliters and 20 milliliters, so that's going to be 170 milliliters. So 0.028 divided by 0.17, oops, 0.028 times 0.17, not times, there we go. Concentration is 0.165. And because this is a strong acid HCl, we assume it reacts with water to completely produce the same concentration of H3O+. So we can calculate the pH directly. So I can just log that, and I get 0.78. So it's very, very strong pH, a strong acid here. So I was titrating a base with an acid. My pH came down fairly quickly, so that at equivalence my pH was only, what was it here? 8. At equivalence, when I was swinging through, because I had that conjugate of a weak base, a weak acid, still available, my pH went all the way down to 4.6. And then as the HCl came over, my pH dropped all the way down even below 1. So that's what it looks like when you titrate a weak base with a strong acid.